So, hello again. Let us continue. And now we are going to talk about some models we are using to describe signals. Wait a minute. I was promising you a little bit more information about terahertz range. So yes, basically the idea of the terahertz range is that it's something in the middle between the radio waves and the infrared. And well, it's used mainly in the medicine and experiments and things like that. Also in space, yes, because at this range, as you imagine, if the wavelength is in micrometers, each single dust can actually be challenge to the wave as an obstacle, and therefore the more polluted is the air, the more difficult it is to actually transmit the signal over longer distances. So in space, it's easier because there is a vacuum, and otherwise, the distance which will be used for signal is not so long. So yes, and here are some also challenges. Well, I might actually share this link with you so that you can later read it, because it's not in presentation, and you can read more at this link yourself when it's convenient to you. But mostly, as it's said, yes, it's used in medicine for scanning tissues and so on and so forth. Yes, so for some cancer analysis detection, in dental imaging, security also, yes, for search of explosives, yes, and so on. Scanning. So basically, it's really similar to X-ray, but it doesn't have ionization, so it's not so harmful. But of course, there is a lot of things more to do. Spectroscopy, which means that we can analyze, for example, to see moisture, yes, levels different, and so on and so forth. So yes, it's experimental, but maybe in future it will be something we will use daily. Yes. Okay, so let's go further. About models. So models, these are some sort of mathematical representations of our channel. So we have this channel, and well, actually we already used a model of the channel in our practical exercise. This was called AVGN model, additive white Gaussian noise. So as I was telling you on our first lecture, actually the noise comes not only in channel, it also is added up in the receiver. Each transistor generates its own noise and so on and so forth. But in our model we are using, we are unifying all this noise into a single source, considering that all the noise happens in this source and it is just added up to our signal. In reality, of course, the physics and how this noise affects the signal is not so simple, but it shows good results. This model is quite precise and good, so therefore we are using it. So again, this is one of the possible models which includes only noise. Beyond noise, there are other effects which can happen to our signal during transmission. So we'll see now what other models there can be. We are not going to use these models further in our practical exercise or course project because they are not so simple and also, well, require additional knowledge on methods, how to actually work with these channels. Yes, because these channels require from you some additional signal processing, which needs to be discussed as well. So first of all, I'd like to mention that we can have continuous channel models, which are analog models, and discrete channel models. So far in our practical exercise, we worked with continuous channel model. But in, I think it will be last practical exercise, we'll try to use discrete channel model as well. that is basically what is the difference here. For example, consider the phase shift keying modulated signal. So we have phase shift keying. So here we have starting from 1. So this is symbol 1. And in other color, I will write down symbol 0. So here we have see the phase changing on the signal. Yes, again, maybe. Well, okay, maybe next one will be also 0. And so forth, yes. And we actually add noise to this signal in continuous channel model. So we generate this signal, and the noise is added to this signal. Now, in discrete channel model, we don't generate this signal, but we'll rather represent signal 1 and 0 as opposite phase signals, like 1 is -1 and 0 is +1 and +1. And we add noise to these numbers. So instead of this signal fragment, we now take only single number, be it -1 or +1, depending if it's 1 or 0. And we add noise with a little bit different strength. Yes, it needs to be calculated, correct strength of the noise, but still it's possible to do. And we add noise to this. So the simulation will work much faster. I will actually show you when will be at the end of our course the difference in octave. It will be noticeable by the eye, and well, hopefully you'll understand. Not for each modulation type it is possible to do. For binary phase shift keying, for quadrature amplitude shift modulation, yes, it's possible to use. For binary frequency shift keying, it's not so easy to use, so we'll be forced to use continuous channel model in our course project, just because 2 out of 3 modulation types require this model. And phase shift keying could have been used with discrete channel model, but well, we don't really want to make it a little bit different for different modulation types. So we'll go with this continuous channel model in course project task 5 or 6. I don't remember what was that, but it will be later. So if it's clear difference, then let's see what are types of continuous channel model. First of all, we have ideal channel model, meaning that the signal at the output of the channel is exactly the same as in the input. So nothing changes with our signal. Of course, as you imagine, this is just a theoretical model which we may use under certain assumptions, but in reality, of course, signal is always one way or another is altered after it's transmitted in the channel. So the next channel is a Gaussian channel, which is one of the most widely used channels. And basically, we are also using it in our practical exercise. Next is addition to it, that we have unknown phase. So this is basically same Gaussian channel with additional conditions, yes, which in certain cases can be omitted, in certain cases needs to be considered. So basically, we need always to remember to choose correctly from these models. Well, that describes better our scenario. And lastly, we have fading channel model. Well, of course, these are by no means the full list of possible models, but these are somewhat like most commonly used ones, yes? So for fading channel, we have multipath effect, so meaning that we have signal transmitted from here, for example, we are receiving it here, but at the same time, this signal is also reflected from some objects, and we have copies of the signal interfering with our direct signal. And this can actually be a bad thing for us. So we'll see how it works. And it's called intersymbol interference, or ISI. I will accordingly show you what's the meaning of this ISI and maybe how we can fight it. And for discrete channel models, we can have the models without memory and with memory. So the memory effect basically tells us that, for example, if we transmit data like this, for example, yes, in the channel, then the symbol which we are getting now will actually be depending on current symbol, on previous symbol, and on another previous symbol. Yes, so there is some memory effect. Yes, as if channel tries to remember what data was passed through it, and well, this actually is the direct alternative to this fading channel continuous model. So you can say that this is fading channel discrete model, yes, to some extent. Okay, so let's start with ideal channel. Ideal channel doesn't have any noise, but it has limited channel bandwidth. So meaning that we have some spectrum of our signal. So for example, let it be the spectrum of the binary amplitude shift keying signal, which we have calculated previous time. And we have some limits on this spectrum, so that only part of the spectrum is inside our frequency band. Yes, so we are using band limited channels. So everything that is outside of this band is attenuated and lost, basically. Yes, for that we need to use filter device specifically, and also we have a constant gain, which is usually smaller than 1, meaning that the signal traveling over the distance becomes weaker. So basically we can have here, for example, 0.5, 0.1, and so forth and so on. This means that the signal at the receiving point is actually attenuated. Yes, it's smaller than it was during the transmission, which is understandable because signal travels some distance, it loses some energy, and well, accordingly, we receive weaker signal than we transmitted. So this is this multiplier. And in addition, we have this traveling time, because even though the electromagnetic wave are traveling with the speed of the light, it still takes some nanoseconds, microseconds, picoseconds, depending on the distance. And this can be considerable time for the system. So sometimes it needs to be taken into account as well. Even with the speed of light, it's still taking some time, very small time, but nonetheless, and it needs to be taken into account. So received signal is attenuated and delayed in time band limited signal. So if we don't have any delay, or for example, distance is very small, which can be happening, I don't know. For example, in your computer case, you can have some cable connecting your hard drive to motherboard. Yes, the distance here is very small and the delay is, well, basically almost non-existent. Your processor and your software will introduce much greater delay there. So there we can consider that delay is small. But if you are transmitting, for example, in mobile communications, 2G standard, which produces the maximum range of the cell to 35 kilometers, actually, yes, then if you are happening to be somewhere here, it will take some time for the signal to travel. It's possible to calculate it, yes, just by dividing. Divide 35 kilometers with speed of the light, meters per second. So this also needs to be converted into meters, yes, and then you'll get how long it will take for this signal to actually reach this mobile device at the edge of the cell in 2G standard. So, okay, but this is a simple model, too simple model. To real channel, usually it doesn't apply because it doesn't have a noise. Yes, always in our real channels, we are having noise and we cannot really get rid of it in any way. We can only make our signal stronger so that it will not be affected by noise that much, but still noise will be there and will be, let us say, waiting for the moment when our signal will become weak enough because of this propagation multiplier to actually be harmed by this noise. So, before we go further to noisy channel, let us discuss a little bit more about this band limited signal and how it's affecting our signal. So basically, this ratio, how signal is, let us say, so attenuated, so diminished, yes, is depending on frequency. Not each frequency needs to be diminished by the same amount. So we can say, for example, that 1 gigahertz will have the ratio of 0.5. 10 gigahertz will have ratio of 0.01. So basically, signal of 10 gigahertz cannot be transmitted because it just loses energy too fast, yes? And 1 gigahertz may be somewhat acceptable. Well, this may be per kilometer, because each distance, the longer is the distance, the greater is this number. The smaller is this number. It's understandable, yes? So this is called the frequency response of the channel. So if we have this channel, we can find its frequency response depending on the frequency. As it turns out from the name, this shows how different frequencies are traveling through our channel. And this is usually a complex frequency response. Yes, so we have complex numbers here, which has absolute value and argument. So the absolute value is called amplitude, and the argument is called the phase. Yes. So if we want to have ideal channel, then we need to have strictly constant amplitude response in the frequency band of our interest. Yes. Outside of it, it may not be the constant, but inside the band delta F where our signal is being transmitted, it needs to be constant, flat. Yes. And linear phase response. So here you can see this phase response is not really linear in this band, yes? So this is not ideal channel and it will introduce some distortion. Now in this line, we can see the ideal signals, basically phase response, yes? And this is actually what introduces this time delay, yes? And this time delay for different frequencies can also be different. So you can see a little bit more technical information following this link, yes? So here is some descriptions about linear system and so forth, about bandwidth, yes, how it affects transmission rate. We'll talk about it also later. But here we want to know about the frequency response of linear, of ideal system. Yes, this is actually the picture I have taken from here. And we'd like to see here this delay. As you can see, we have two different frequency signals. We have frequency 1 Hz in this picture, and in this picture we have 2 Hz. And you can see that this delay is different for these two signals. So red is original signal, and blue is the signals that has passed through channel, yes, and it has been delayed by minus p divided by 2 phase shift, yes. And here it also, the phase shift was minus p divided by 2. However, expressed in time units, in seconds, yes, this is smaller time. So this effect is like this. So we cannot really have constant phase delay. We need it to be linear, to be increasing. So if therefore that would be linear delay, then we would have here minus p, and that would produce the same delay, because we need to consider that our signal, for example, rectangular pulse, consists of multiple harmonic signals. So, for example, harmonic signal number 1, harmonic signal number 2, and if we add them up together, we'll get, for example, something like this. And there are even more these harmonics, which ultimately will generate this rectangular form. So in order for these rectangular poles to be still rectangular poles at the output of the signal, each of these components must have the same time delay. Otherwise, some components will be earlier, some components will be later, and this can lead to the distortion of the signal form, meaning that these rectangular poles will no longer resemble rectangular poles. So this is actually quite important, yes? So you can study this material more. It also provides some insight about signal-to-noise ratio and so forth, but we already discussed that, and we'll discuss this more when we get there. So this is for ideal channel. Now, for the Gaussian channel, basically what changes is that we just add noise into this equation, and that's all. We still have these frequency response requirements, flat amplitude response, linear phase response, yes. And in addition to that, we add noise. So this is quite good model for cable channels or direct line channels, radio channels. So noise is a random or stochastic process, yes. So basically, it needs to be generated somehow. If we are making some simulation in nature, it's just a random process with Gaussian distribution, as you already know, and it's called white noise because it's completely random. It doesn't depend on previous values. So we already did this in practical works, yes, number 1, number 2, but we did have some assumptions. So here we can see that we have this gamma factor and this tau delay. So in our practical exercise, we just assume that we don't have really any attenuation caused by the traveling distance. Well, this is possible if we don't have long distance. Yes, and accordingly, if we have short distance, I mean, sorry. And accordingly, if we have short distance, then also traveling time will be insignificant and can be not considered. But in full model, these parameters may need to be considered, yes? So next step is Gaussian channel with unknown phase, yes? So what changes here is that this time delay is no longer constant, yes? So basically this tau can now change. Well, this may arise some questions, but how can it change if we have, for example, frequency, let us say 1 gigahertz, if we have distance 1 kilometer, which is fixed, yes, so that means that this tau has to be constant. Well, the truth is that our generator never produces constant frequency, so this can be unstable. Yes, this is the generator's property, because generators include some components which are depending on the temperature. So mainly each generator should have resonance contour, yes, which includes capacitor and inductor. And as you know, as the temperature changes, so does change the inductivity and capacity of these components, and the frequency is actually depending on these parameters. So therefore, frequency will change as well. It will fluctuate. So that will also change this time, yes. Also, the channel itself can change this parameter. We already discussed this phase frequency shift keying, yes. So if this phase response is something like this, for example, yes, then it will also make this as a variable time delay. Basically, this is the most common reason, yes, because stability of generators is something we can address. We can use more stable, more precise generators. We can use some compensation techniques, some regulation systems, and so forth. But usually, channel is outside of our control, especially if we are talking about some mobile communications, about moving objects and so on in city environments, then that's basically not what we can control, yes? So most commonly, this is caused by those non-linear phase shift keying. Phase shift, phase frequency response, yes? So, yes, we already discussed such a thing as analytical signal, yes, as a Hilbert transform represented. So we can actually make it as a factor, this delay, yes, instead of writing this as, well, here you can see that here we have this time delay inside. So this is our theta, yes, inside brackets of the signal, and we can factor it out outside of brackets if we use this analytical signal as a component, separate component, yes. And this is a random number. So theta is random in range from 0 to 2p. Each time it changes, yes. So this is just a formula for this model, somewhat more convenient. Yes, it may not look right now because we don't really have any practical task to check it in, but if we would have practical task, then we would note that it's much more difficult to use this formula than this formula to actually get some results. So for this channel, this is close to real channels, yes, radio channels, but still not really full picture. Yes, the full picture is fading channel. So the fading channel is basically having not only random time delay, but also a random this component. So this is happening because we have in real world different obstacles, buildings, cars, trees, everything that produces reflected, diffracted signals and so on and so forth, which interfere or distort our original signal. Yes. So what is happening really? Yes. So consider that we have mobile device which receives signal. We have this direct wave signal receiving, but considering that this emits radio wave in all the directions, yes, we will also receive at this point some reflected signal from this building, for example, and from these mountains somewhere there, yes, and some diffracted signal. Diffracted signal will try to walk around this house, yes. It will change its direction. It will not be a direct line. It will diffract, yes. And all these signals are received here. So they also have different strength and different delay. As you can see, this signal is the fastest signal, the signal which we have received first, because it's traveling the direct line. Yes, this is the shortest possible distance. All the other signals are longer path. Yes, this is longer path, this is even longer path, and this might be the longest path. Yes, so accordingly they are having greater delay. And what happens in the received signal is that we add them up together. So we receive this composed wave. And for that signal, the spectrum, as you can see, is no longer having the flat amplitude response. Yes, so original signal had flat response. The received signal has this selective fading. So this fading is actually observed here. That signal loses its strength, specifically at some frequency f1. Yes, this is some sort of peak in this response. This meaning that this particular frequency, due to these geometrical properties, is propagating much worse than other frequencies, and this can distort your signal and make your data unreadable. So this is intuitive description. Yes, you can see more about it here. This is how real measurements actually look like if we connect a spectrum analyzer to signal. Yes, you can see that non-faded signal has more or less constant level, and faded signal has some fluctuations here. Yes. Similarly to constellation of the received signal, basically, yes. For non-faded signal, we can clearly distinguish separate points. But for faded signal, these points are making some circles and so forth and so on. Again, we will not delve into deep details in this course. I'm just providing this information for your knowledge in future courses, because you might come in handy with this. Yes, so here are some mathematics more if you are interested in it. Yes. Here is what happens with this signal. So consider that originally our signal was this, then we have some copies, and then after receiving all of them, we receive something that is not this signal which we wanted to transmit. Yes. And basically this changes the spectrum and so on and so forth. Also, this has some codes for MATLAB, which you can execute if you'd like and see for yourself, change some parameters maybe. Yes. Also, if you have any questions about this, you can ask. And this also provides some insight into MIMO antennas, which is well outside of our course, but still may be interesting for you. Okay, so for fading channel. So as I have told, for fading channel, we have multiple signals. So basically, each of these signals, which you can see as line here, will be now more or less this Gaussian channel with unknown phase. And in addition, no. This will be changing because of this sum. So here we have nice explanation video. I believe we should watch it completely. It's just 5 minutes, and it will shed us some light how we can go from the Gaussian channel to this fading channel. So let's listen to it.
Sorry, we don't have the sound.
No sound?
Yeah, we don't have the sound of the video.
Oh, that's odd. Now also not?
Nope.
Okay, maybe you can run it on your computer to listen. I will not comment for now. And then after it's ended, I will also share some comments about it. Okay, so let us then start. And I have put the link in the chat for you, which you can follow to open it up. But it's weird why sound is not working. I will see into that later, but okay. So, yes, now I'd like to add some more explanations. Actually, this is quite good channel, I believe. Yes, you can see more videos there. The last thing about fast and slow fading was basically related to these values. Yes, whether they change fast enough depending on your data or slowly. Yes, and that also makes fast and slow fading. But okay, this is one signal gain. Yes, so this is random process. So previously in Gaussian channels, we had this as a constant. Yes, you can see this was actually a constant and only the phase was changing. Now in fading channel, actually this is also a random process and it's complex and can be described as this is description. So we have this alpha modulus and this argument, yes, where di is distance of that particular path. So this path will have distance d1, this path will have distance d2, which are similar, but a little bit still different, right? And d3 and so on and so forth. And depending on this distance and this random gain, this is also random. And this is the path of one channel. Now we are going to put this path into this expression, yes, and consider that we have actually multiple paths, yes. So here, wait a minute. What we are trying to do now is, so this will produce as gamma 1, this will produce as gamma 2, this will produce as gamma 3, and so on and so forth, yes. But what we try to do is now to find out what is the total gamma for the entire signal. Basically, this is very simple. We just add them all up together, where L is the number of this signal. So in our particular case, L is 1, 2, 3, 4. Yes. And for each of them, we have this random process, which produces this random total multipath gain. Yes. As it was described in video, if you add up multiple random processes, and this is a random process, and actually it's not really important what distribution we have here, distribution can be different, but if you add up enough of these numbers, then you end up with normal distribution, with Gaussian distribution. This is called central limit theorem. Yes, you can watch it up on Wikipedia, for example. And that's why actually normal processes are so widely distributed in the nature, because even for, I don't know, some social aspects of our lives, each random event is a result of so many factors, so many different factors which are also random, that it's actually summing up together into the random or normal process. Yes, so this is some statistical properties. Yes, so this is random normal process. Yes, now the absolute value of this random process has Rayleigh distribution. How does this happen? Well, basically this happens because our random this gamma has random real component, real gamma I, plus random imaginary component, imag lambda I. Lambda MP, sorry, lambda MP. So this is a complex number. Well, complex number is calculated as absolute value of the complex number is calculated as real part squared plus imaginary part squared, right? And square root. And this results in the Rayleigh distribution if this is Gaussian and this is also Gaussian, then the result of such a absolute value calculation is this Rayleigh distribution. Rayleigh distribution has this so-called long tail, yes, because Gaussian distribution ends are fast here, but this Rayleigh distribution can actually continue like this, yes, and it's also not really symmetrical. You can easily try for yourself this in the octave, for example, and get similar pictures to make sure that it's actually true. Well, in fact, I can show you very fast, yes. We just need to generate, let us say, X as a random normal process. 1 minute, please, help. See how it's generating. So we need to generate a rand n, say 10 numbers, yes. So let's generate instead 1000 numbers as X, 1000 numbers as Y, let's see if it's indeed a Gaussian process. So for that we are using the histogram function, hist x. It displays, well, we can change number of beans also to be more detailed picture, not 10, okay, 20. Okay, this looks like a random Gaussian process with 0 average. The same goes for Y. Now we are going to make Z as a complex number. So real part and imaginary part are both Gaussian process, and histogram the absolute value of this Z. And you'll see that this is actually a Rayleigh process, abs Z. Yes, well, we don't have much numbers. If I would have 1 million numbers, then it will be much more smooth, but you already can see that here we start from 0, not -2, because here we had -2, yes, so basically we are going to have almost like half, and this is a little bit shifted. So this is the property of statistic, and that's why it's called a Rayleigh fading channel, yes, because the absolute value of this attenuation multiplier is variable and random process with Rayleigh distribution. So there, as it has been told, can be fast fading and slow fading. With blue line here, you can see normal loss of the signal power over the distance. So the farther is the distance, the weaker our signal becomes, right? And here, with magenta color, you can see shadowing effect, which is the same as for the slow fading, which happens when a signal has some obstacles, yes, that are making like a shadow on our signal, preventing it from going into direct line of sight. And you can see that this is actually has some slow oscillations depending on the distance, right? And fast fading, as it occurs from the name, is having these oscillations much faster, yes? This is actually the case fast fading, which we are looking at here. So this is some material we are not going to use in our course directly, yes, but still I wanted to show you that in reality this model is much more difficult. So yes, rather than just adding up noise to signal and that's it. On top of that, of course, on top of that, there will also be a noise, which is not yet plotted here, because basically we have been discussing only this gamma, which is then put in here. Yes, that's where we put that gamma as a variable process. This is also a variable random process. And there is also, of course, always noise. It doesn't go anywhere. So these are models for fading channel. And this fading channel is actually the reason why intersymbol interference happens. So what is this intersymbol interference? Well, as it occurs from the name, this is the scenario the case when our data interferes with itself. So the idea is very simple. Consider that here we have three paths of our signal, yes, and we are sending some symbols A, B, C, and D to our mobile device over different paths. So path 1 is the shortest one. So this signal will arrive first. Yes, it's here. Path 2 is longer, and it will take more time for this signal to travel. So we'll receive the same data, but a little bit later. Yes, here. And path 3 will be received even later. So what is observed here is that actually direct signal symbol A ended here and started next symbol B. At the same time, the delayed copy of the signal still has symbol A in this interval, which will interfere with our B symbol. And therefore, this will lead to some distortion of the signal. Yes, that is the problem of intersymbol interference. And this is basically happening because of these reflected signals. Yes, so we need some measures to work with that. Okay, so here is more information about it, which you can see. Yes. And one of the possible solutions is actually to add prefix to the signal. Yes, special prefix, so that this part of the signal will be, well, repeated. Yes, let us basically say. But again, another possible solution is to use advanced signal processing, modulation called OFDM, which is actually used in Wi-Fi networks and LTE as well. Yes, and which prevents this from happening. And also there is a thing called equalizers. Which can also help us with to fight this problem. So nothing of this will be discussed in this course. I'm just wanting to, I want you to have more complete picture of what is real communications like. But eventually, after finishing this course, you will be capable of working in that direction in next courses, which may will later, or during your own work, yes, on these problems. So yes. Okay, now for discrete channels. Discrete channels are quite simple, yes, and the idea is also very simple. We'll discuss it with a binary channel, meaning that we have only two possible symbols, 1 or 0, but this will work with non-binary channels as well. It will just have more of these blocks, yes. So the idea is very simple. Discrete channels are operating with either 1 or 0. So everything that is between is basically rounded to closest symbol. So there can be 4 cases. So first case, we transmit 1 and we receive 1. This is normal, yes. Second case, accordingly, we transmit 0 and we receive 0. Each of these cases has its own probability. So probability of receiving 1 when 1 has been transmitted, and probability of receiving 2 when 2 has been received. Adding up these two probabilities together will give you the probability of the correct reception. Now there are also 2 cases when you have sent 1 but received 0, which is error, and you have sent 0 but received 1, which is also error. Each of these cases also has its probability, and not necessarily these probabilities will be the same. There are some communication systems, for example, binary amplitude shift keying, where these probabilities are different. And in sending this signal over long distance, we will much more often have this received as 0 rather than this 0 will be received as 1. Yes, because it's already a no signal, yes, and noise needs to be just so strong that we will receive 1 here, which is also possible, of course. So If these probabilities are equal, however, then we are talking about symmetric channel. Symmetric, yes. So this can be symmetric channel as well. We'll return a little bit later to this model when we'll calculate the error probability for your course project, but it will be later. Yes, not now, not today. We need still to discuss some more material before we go there. And discrete channel with memory. Discrete channel with memory, as it states from the name, has some memory effect, which is basically the fact that if you have received symbol with error now, then it might have error in next symbols as well. This is this memory effect. Channel it as if remembers previous symbols. So error probability for channel with memory depends on symbols received correctly for symbol sy plus 1, which is now, yes, so you receive symbol now, and there was one symbol before. So whether we will have error here or not actually depends not only on noise, but also on the fact if we had error here. So basically, if we had error in previous symbol, then it's likely to have error in the next symbol as well. This is the effect of memory, because this error is maintained in the channel for some duration and affects multiple symbols, not just one symbol. And such description is actually discrete channel for intersymbol interference effect. Yes, and we can use Markov models for such description, which is basically represented by this matrix, where P1 is conditional probability to receive symbol now correctly when symbol before was also correct, yes, and P2 accordingly is conditional probability to receive symbol now Si when previous symbols before Si minus 1 was also received incorrectly. Yes. Wait a minute. So here we have probability to receive with error. If previous was without error, that is P1, and probability to receive with error if previous was also with error. So that is probability of error, and accordingly this is the probability without error, 1 minus P, yes, opposite event. So yes, again, we will not really use this model, but I wanted just to have you a complete picture about these models. So okay, I believe now we can, after this rather mathematically intensive material, have a little break, yes, again for 15 minutes. So we continue at 10:40, and then we will conclude the remaining 13 slides. And when we finish, then we'll be free for today. Yes, so thank you for attention and see you in 15 minutes.